We're now ready to implement type checking in terms of this language. Our language is the same as usual, lambdas with single arguments. Notice we've adjusted the syntax though, where we have to say for each argument what its type should be. And that means that we need a grammar for writing down types. A type is either literally NUM or BOOL, or it's an open parenthesis, a type, an arrow, another type, and a close parenthesis. So if we take this grammar and turn it into data structures, our expression data structure looks the same as usual, except that in a lambda where we used to just have n and body, now we have n and an argument type and a body. Right? An argument type is an instance of type, which is either a number or a Boolean or an arrow, where an arrow has the left side of the arrow, which we call the argument type, and the right side of the arrow that we call the result type. We will also need type environments, which we wrote as gammas in the rules before. That's very much like environments in interp. It's just that it maps names to types instead of names to values. So we'll put those things together into a type binding, and a type environment is just a list of type bindings. So our type check function takes an expression and a type environment and produces a type. If it can't produce a type, then it raises an exception, which means the expression has no type. So A is the expression, TM is the type environment, and we do the usual type case on expressions. If the expression is a literal number, then our rule says, our type rules that we worked up before, says that any number expression in any environment simply has type num. And the way we represent this type is with num_t, and so that's what we return from type check in that case. In the case of a plus expression, we have two sub-expressions, L and R, and when you have an expression, the immediate thing you do in type check is call type check. That's what you should expect to do. Type environment tends to go along for the ride. Well, it's being accumulated, but there's nothing to accumulate in plus C. And now let's look more at our type rule again. Right? These recursive calls are shown here, where what this says is we expect that we get a num back. We need to make sure that we get number types for both the left and the right expression. So we can do that with the type case using type on the result of type check. As long as the left expression produces number type, we're in good shape. Otherwise, we'll use a type error function and complain that L doesn't have type num. In the right-hand case, then we type check, and if that also has type num, then the whole plus expression has type number. Otherwise, we complain for the right expression. Right? So this num_t here is that result, which we get to only if both of the sub-expressions had type number. Multiply is the same, so in fact, as you'll see in the code you can download, we just lift this out into a helper function that both plus and multiply use. So let's move on to identity. Let's move on to identifiers. So when we have a particular identifier with this name, the rule says you have to go look in the type environment to find the type. So here's our type environment TM. We're going to need some type lookup function that takes the name in the type environment. And that's straightforward to write. It's the same as lookup. In fact, in the code that you download, we abstract over lookup and type lookup into a make lookup function. That brings us to lambda, lambda forms. So in a lambda form, you see the main thing we need to do is type check the body expression, right? So whenever you have a body, whenever you have an expression, you expect to type check it. But we can't just pass TM here because on the left of the turnstile is not the same gamma that we had before. Right? Remember, this gamma colon is just a funny way of writing the word type check, where the arguments have been written backwards also. This is the first argument, this is the expression argument, this is the type env argument. And what this says is in the recursive call you use the sub-expression, but also extend the type environment. Very much like interp, we will extend the type environment. Right, we can just use extend_env for type environments as well as environments. On TM, where we bind the name in to the type that's written down here instead of to a value. Now, notice that this is different from interp. In interp, for lambdas, we just created a closure. We didn't recursively interp. But this is how type checking differs from evaluation. We do just recur on the body when we're type checking, because it doesn't matter how the function is going to be called. Either the function has a type or it doesn't. Once we've done this, once we type check the body, we get the tal2 here, and we need to put that together with an arrow. And this is the second part of the arrow. And the first part of the arrow is the tal1 again that we wrote down here, so that's just arg type. So this is producing the arrow, tal1, and then tal2. Finally, we have applications, where we have two sub-expressions, so we type check both of them. As the rule says, passing along just the existing gamma as we had it. And now what we have to do, according to this rule, is make sure that the type of the first sub-expression is an arrow type. So we do a type case there. And we should get an arrow t with an arg type and a result. Otherwise we complain that it wasn't a function type. Now that we have an arg type and a result type, we can also type check the argument expression, see if it has tal2. So tal2 being the result type, we need to make sure that this thing and the result of this expression are the same. We can just use equal to compare those. So we compare the argument type to the type of the argument expression. If those are the same, then the result of the application is the arrow type's result. So that's why result type here goes as the result. If they're not the same, then there is no type and we have to produce an error. We say that the argument doesn't match the expected argument type.